conduct. Yeah, so we are the Asia User Group Eldoret, and this is a dedicated group to fostering a thriving, respectful, friendly, and professional experience for everybody. We welcome and support all members in a safe and inclusive environment where everyone can scale to cloud together. So, what are some of our core principles? The first one is the purpose. We purpose to be an inclusive, safe, collaboration, and professional growth for all. Um, Apart from that, we also welcome people from all backgrounds, genders, races, and religions. And another thing we really uphold is being friendly and respectful, in that we listen, we provide the space, and we use kind language in our communication. Also, in the spirit of that, um, in our professionalism aspect, we listen and avoid criticism. So this focuses on building bridges and not personal attacks on people. So we also don't spam, or we don't we don't do spamming. We protect privacy and we focus on continuous learning. I'd like to welcome everyone to today's session. That's Kubernetes HA database strategies for cloud native resilience. And our speaker is Mayank Gupta. He's a senior research and development engineer, level 5 at Boardroom. Yeah, Mayank, thank you very much. And over to you.
Sure. Thanks, India, for the introduction. Yeah, hi guys, this is Mayank, and I have close to 20 years of experience in the database clustering and cloud native infrastructure applications. So that's where our today's topic is. I'll quickly share my screen. Do you hear some drum sound? I could hear that. I would recommend if everyone, can go on the mute. Okay, let me know once you see my screen. I hope that is visible. Can you guys see my screen?
Yes, we can see your screen.
Okay, all right, nice. So we can start. So today's topic is about how to handle the database clustering on the cloud native environment, and it's a Kubernetes-based solution. I'm sure quite a few folks here have gone through the database problems, they have faced the database issues in their tenure. Basically, the legacy applications will have the standalone single databases, and the need of the hour for a highly available application is to have the cluster database on the cloud with the help of Kubernetes and other under the hood strategies. So this is where I'll touch base on my topic today. And during the topic, I'll talk about all the basics, not all the basics, but few basics of the database cluster, how it goes on the Kubernetes and cloud, and a few strategies around it, fundamentals, a real-time solution with the help of a MySQL provided solution, which is MySQL InnoDB cluster, which is ready to use solution provided by Oracle, and kind of certain scenarios around it. So that's the agenda we'll cover today is the high availability fundamentals, what it takes, and the clustering architectures, how we can deploy our services, how we can distribute, how we can set up the multiple components around it within the cluster to have different aspects or different flavors of our cluster. Then the example as MySQL InnoDB cluster, which is again Oracle provided solution. Then the Kubernetes enhancement on it, how Kubernetes is handy and how it acts as a monitor of the class to handle the failovers and other upgrades and key scenarios. Then I'll showcase how the failover in action will happen, how the recovery will happen, and then few operating scenarios like how DevOps people can handle it. So mostly it's about theory, not about the code. And if you have some database experience, that's well and good. If you have some Kubernetes experience, that's pretty handy. But if you don't, then don't worry about it. It will be the basics, and I'll start from principle one of all the components. So what do we have right now? Let's say our most of the legacy applications have a single database. That is, for example, in the picture, we have a diagram where on the top blue, we have the application server, which is talking to a database, which is a typical scenario for a service client application. And then the problem here is that our database is a single point of failure. It's just a single instance. So if something goes wrong on that database, then our application is kind of down too, because application will not have any data to respond, so it will not work. On the right side, on the red tiles, I have noted down certain failures which can impact the database, and basically due to which database can fail. So the first one is one box, one blast radius. If something goes wrong on the box itself, some out of memory exception, some disk have some exception, something goes on the server, so automatically a database server is down. And then the second is like failover is a human process. If we have a single point of failure, then if something happened, then manually someone has to intervene and detect like what went wrong, and then they have to accordingly decide, or we mostly they have a replica on the standby, so they will promote that replica to be a main DB, so that application will resume their processing. But that human loop has some delay, some detection, some human prone errors, so those kind of scenarios can happen. The downtime is the main thing that hurts here. So the longer the server is down, longer the application will be down. Then the legit problem is what happens in the peak days. If we have to scale up the database, if we have to scale up some kind of performance, then it's always on the hardware. If we have to scale up the services or the database configurations, we have to bump up the hardware. Then again, we have to logically call for a downtime. Then the fourth one is the regular maintenance. What if we have to upgrade the database version itself? Let's say MySQL is running on some 8.4 something version, and we want to bump it to the latest version or some XYZ version. Then automatically we have to bring down the server for the upgrade cycle. It could be the server upgrade, it could be the schema upgrade, it could be any upgrade on the database, but that calls for a downtime because this is a single database. So the single database is the main problem here. And the solution is that we can have multiple layers or multiple instances. That is database cluster. We call it database cluster. And in the next picture, I have database cluster, which is a very basic architecture diagram of a database cluster, which is nowhere close to production application. But just to make it simple as a comparison to the previous diagram, I have depicted it here. On the top, we have the application server, which is supposed to connect to a database, which is a multiple instance at the bottom blue. But now we have a middle layer between them, which is the router. So first of all, at the database, if you see, there are multiple nodes, although there is only one primary node, which is actively responding. But even then, if some failure happens at the database, we still have some replicas to respond. So the failover will be faster, and with the help of router, application will never realize that something has gone wrong on the database. So application will always connect to the router. A router will internally identify whether out of three database nodes, which one is working, which one is active, which one is primary. So based on that internal information, it will identify the node, which one should respond. The main goal is that the database should not go down at any point of time. Even for the upgrades on the like we have the tiles on the right side, there is no single point of failure here. Failure is automatic. Router will chime in to identify the secondary node if the primary is down. If you want to scale up, we can scale up the secondary nodes at any point, and then primary is still responding. Once the secondaries are at a point that they can take over, router can just switch from primary to a secondary node, and that's how it will happen in seconds. Again, for the last one, which is self-healing zero downtime. If you want to upgrade any database, if you want to upgrade the schema, we don't have to upgrade all the nodes at once. We can do it one at a time. And in that scenario, application is not suffering. Application always have at least one database node that will respond. So we are covering all the four boxes here, which is the fundamental of high availability on database cluster. So these are the again fundamentals of cluster. Like how do we measure like whether a cluster is capable of doing something? How is it like where do we stand that cluster? How is it working? The functionality and the response time. So the main terms that goes around it is RPO and RTO. RPO is uh, it's actually recovery point objective, which is the point where it can go. So every database has a sync point, like up to which all the transactions have already committed. So if a failover happens, then there is a gap between the previous save point, between the previous successfully committed transaction and the current failure point. So that's a gap that has not been synced in the database. And then RTO is recovery time objective. Like from the time of failure, how long it can take to recover. So longer these 2 points are, longer these two matrices are, that means our database is not up to a grade. For an ideal scenario, we want to have zero RPO and zero RTO, or maybe in milliseconds. So whenever there is a failure occurs, if it can automatically recover within milliseconds or within no time, that's the ideal scenario. Same goes with the RPO. If we are syncing all the data in real time, then technically we are not losing any data at the time of failure. All the replicas are in sync. They have exactly same data what their primary has, but it's very hard to achieve. There is a cost associated to it. I'll talk about those things, those factors, but right now I just wanted to say like these are the things that's desirable for a database. Then the other four fault domains that we always want to cover with the database cluster is a node failure. What will happen if a node fails? Is there any replica ready to be used, or is there any kind of backup we are having here? Again, RTO, RPO, how long is it going to take to recover? Uh, how much data we are going to lose? So node failure can have all those questions. So our database solution should answer it. We should plan it in a way that the node failure is automatically taken care of, and so that we have minimal data loss. The storage failure. Database is all about storage. We are storing the data. What if the whole site, the whole cluster goes down? The storage should not go down. Database is for persistent, and basically if data goes down, then there is no use of having a cluster with high availability or high usage if the data itself is at risk. So there are solutions to that. We can have multi-region cloud, or multi-cloud deployment where our storage is segregated or is deployed at a different location, which is not at the same cluster or uh, uh, same cloud where our application or our database MySQL server is. So that's how we can distinguish or segregate data and the server. Then the network partition. Network partition means whenever there is a network glitch, if nodes are not able to communicate to each other, then what should be the behavior? In this scenario, for example, if there are multiple nodes, like let's say there are 3 nodes in a cluster, and all 3 are available right now. The first one is primary, other 2 are secondaries. So this is a typical scenario when database is working fine. What if both the scenarios, both the secondary goes down, we only have the primary node? Then technically database can respond to the application and nothing is wrong with that. But we have to set a quorum that database should stop responding in this scenario because there is no replica. As of now, primary is responding, but what if the primary itself goes down? There is no replica. No one is having a backup of this primary. So the quorum is at least there has to be a minimum 1 replica to the primary node. Otherwise, database cluster should not be up. It has to be fixed. So we configure all these things with the help of Helm chart, with the help of Kubernetes configurations in the Kubernetes environment, and that database Helm chart itself will have that protocol that database has to have majority of the nodes available. Otherwise, it will be termed as failure or it is down. Then the zone. Like we can have multiple zones, we can have single zone having all the nodes, all the pods, but there is a risk of failure or disaster if all the sites in the zone are down. So that's why the multi-cloud structure is highly recommended, especially in today's scenario where all the applications are supposed to be highly available with database consistency and all durability. So durability can only happen when we have distributed the database or the persistent layer geographically in a different locations. So that's how we can achieve with the cloud. If you have any question at any point, please raise your hand or maybe you can note it down and I can take those questions at the end. So these are the mechanisms how we can divide how we can structure our database nodes. So I can talk about this in the next slide, which is the actual diagram of a InnoDB cluster, a Kubernetes-based InnoDB cluster. And this is the solution provided by MySQL. And it is like 70% complete here. I have not shown all the other boxes, all the other components that comes with it to make it simple and readable. I'll start with the left side, which is a control plane. So control plane is a Kubernetes based controller, which comes with in this solution, it comes with MySQL operator. So MySQL operator is kind of a monitor here, which monitors the whole cluster. It orchestrates everything in the cluster so that it functions properly, it replicates data properly, it accepts the failovers, it assigned new nodes to the primary, it makes sure that router has the latest information, it makes sure that backups are happening timely, it makes sure that there is no lag in the system. So all those responsibilities are taken care by operator. And this operator is the main guy which is responsible to deploy this cluster in an order, and at the same time it will manage that desired state. So at the time of deployment, whatever chart, whatever configurations was accepted for the database, operator will just note that as the desired state and at any given point of time it will try to maintain that state. That initially, if we are saying there has to be 2 routers, there has to be 3 DB nodes in which one primary is there, multiple secondaries are there, there has to be a backup. So it will note down all these configurations, and with the help of Kubernetes and other metrics, it will manage that desired state. If something goes wrong, it will it will talk to Kubernetes, it will talk to database internals, and it will maintain the desired state. Then the second component is the data plane, which is the middle layer. Again, the application. So the application is connected to MySQL routers here. which is kind of abstraction. So application is not directly connecting to the database. It is talking to router. Router is, again, you can see multiple routers here. So router has a replica here. So that it can handle a failure at the router level. Router is not a simply a pod. It is actually a service, a headless service, which is talking to the application. So application doesn't have to know that what router is responding. Is it router A or router B? Or if both of them are gone, then Kubernetes or MySQL operator will itself create router C or someone else. But the main point is that service address is always the same. So application doesn't need to know who is responding underneath and what's happening if A is down or B is down. So that's the beauty of it. And the second part is how router is talking to the cluster. Then the cluster, again, the same segregation. Router doesn't talk to the doesn't talk to any node directly. We have three nodes in the picture, but router doesn't want to know like which one is responding. Although it has all the information, it is checking the heartbeat. It is checking the database cluster, like which is primary and which is secondary. But again, that happens with a wrapper. Database cluster is exposed via, again, a headless service, which underneath is supported by the primary database node. In this case, uh, what happens at the deployment time? So we give the configuration to the operator, which is internally happening. Operator will see that there has to be three nodes. So it will spin up first node, which is MySQL cluster 0, and it will load the schema. It will load the data, whatever it has to do for the database regular operations. And once that node 0 is ready, it will mark it as a primary, and it will start a cluster with one primary node. So that one primary node has all the data, everything is there, and that is the main node for the cluster. Cluster is not yet ready. Then the MySQL operator will start other secondary nodes in parallel, which are a clone of the primary. So that way it is making sure that whatever data is there in the primary, it is always there in the secondary. So secondary nodes are always in sync with at the start, they're in sync with the primary node. So they'll have all the data. And once cluster 1 node and cluster 2 node, they both are ready, one at a time, they will join the main cluster, and that's how they will bring the main cluster up with the three nodes. And everything is noted down in the database tables, all the group replication tables. And with the help of those tables, it will maintain like which node is read write, which node is read only. Router at any given point of time cannot send a read write request to a read only node. It is not acceptable. It will not execute. Even though it will try to do that directly, it will just lock it, because cluster 1 and cluster 2 are read only. And that is also an advantage to the router, that if router wants to segregate the data or the traffic from application between read only and read write, it can simply do that. Read write traffic should go to the primary node, and read only can go to the secondary nodes with the help of multiple ports. And that's how it will manage. Then on the left side, we also see a box which is MySQL shell. So why do we have it? The main purpose of this is basically this is an admin API. Whatever a DBA does on the database in terms of executing queries or fixing any failure, or collecting the metrics. So all those things we can do, or even operator can do via MySQL shell. So operator doesn't directly go to the cluster nodes or database to execute any operation. It will go via shell. And via shell, it's quite easier because it exposes internally certain objects, like say a DB object or the cluster object, or it can check like with the help of those objects, we can directly verify the state of the cluster. like cluster dot status. We can check which one is primary. We can check which one is secondary. We can check their IPs. We can check their other details. What's the level of group replication they have. We can also directly query to a particular table. Via MySQL shell, it can also query into a secondary node to execute any sort of query. But again, the quorum or the protocol is the same. There is no read write query that can execute on the read only nodes. So that's how it works. Behind the scene, there are other components that ships with the MySQL solution, cluster solution, which is the uh, secret manager. The secret manager is to handle the secret as a vault, all the credentials and everything for MySQL router, for the cluster, for the DB. If you want to handle those secrets separately from the configurations, it can be done in that pod. There is a monitoring sidecar which actually can be used to monitor the metrics or the traffic or the throughput of databases for the auditing purpose, for the reporting purpose. So that's a separate uh, uh, pod. That's a separate sidecar. And then there is also one layer that can be used between the application and the router. That could be a load balancer. It's ingress or istio level, which can be used to again to have the DNS segregation and to have the routing, to have the load balancing and TLS SSL enabled things. All those things can be handled separately between the application and the router, so that database doesn't have to deal with those NFR things. And then this is the in-depth for nodes itself, how we can handle multiple nodes within the cluster. So there are multiple strategies how it can be done. And let's go back to the diagram. You see three DB nodes here, which is cluster 0, 1, and 2. As of now, there is only one primary. So whatever traffic is coming, it is coming to the primary node, and then the replication is happening here. You see the group replication cluster. I did not talk about it because we have a separate slide for the group replication. But the main thing how it happens here is primary node will get the data or all the transactions, and then it will commit those transactions in the cluster 0 node, and then it will tell back to the router that commit has happened, so transaction is complete. So that's the fastest way or the earliest way to achieve or to commit a transaction. So the transaction is done, but behind the scene, what happened is that operator, with the help of group replication, it replicates the data to secondary nodes, and that can happen in multiple ways. It can happen in parallel, it can happen in async mode, or it can happen in semi-sync mode. So that's what we talk about here. If we have single primary and if the group replication is happening in the async mode, then that's the fastest way to commit a transaction, but there is a delay in the sync. So if there is a failure that happens within the sync time, then there could be a data loss because the secondary nodes doesn't have the uh, transaction data from the last sync. So that's the risk. And it depends on the scenario. It depends on the design of the application or the requirement, because there are certain applications those need the fastest write time. They can bear the asynchronous sync. But then there are few trading applications, let's say, they cannot afford to have any data loss. They need to have all the primaries and secondaries to have the same data. Because in the case of failover, they need to have all the data available on the secondary nodes, and it has to take over immediately. So that's how if we have multiple primaries, which is the fourth row, multiple primaries will make sure that all the nodes, all the database nodes have the exact same data. But the cost of it is like whenever router is writing to multiple nodes, then the write latency is there. Or every time it has to write to multiple nodes instead of just writing to the primary. So the writes could be slow. So that's how it uh, it is like a delay on that side. But we can have a semi-sync, which is the second row, which says whenever there is a primary node where we commit the data, primary will make sure that the sync or replication is happening to at least one secondary node. So if one secondary node is up with all the latest data, then it can commit the transaction. So there is a small delay at the right, but at the same time, it is making sure that replication process is quick because it is happening almost at the same time. It's a real-time replication, not to the whole cluster, but to let's say half of the cluster. So that's how they're balancing it. And same thing we have in the uh, uh, in the failover speed. If failure happens in the primary, then it could take 30 to 120 seconds because operator and router they have to sync, and the operator has to decide that primary is down. So out of two secondaries, which one should I pick to make the primary? And it will behind the scene, it will modify all the tables. It will tell the group replication process that one node is down, don't talk to that, I'm working on it. And then out of these two, one is primary, it will make it read write, it will make the other one read only. So that's how it will take it will do the modifications, and it may take 30 to 40, 50 seconds in that process. For semi-sync, this is faster because one node is almost the exact replica, which is ready to be used. So the recovery is faster. Multi-primary, again, recovery is super fast because all the primary and secondary nodes have the same data. So it is basically very less. Could be in milliseconds if it is done uh, ideally. But the complexity is very high. So on the right side, on the rightest column, we have the complexity for all the mechanism. The cleaner approach is the primary, single primary and replica, so that it has the lowest complexity. There could be a delay in the failover, but it depends on the scenario. The highest complexity is for the multi-primary. There are some conflicts whenever the router is writing to multiple nodes. There could be conflicts. There could be transactions that happened on a couple of nodes, but one is still waiting. So it cannot acknowledge the complete transaction. So that's how we need to design the system based on the requirements. Yeah, so these are the main factors that these are the main fundamentals that happens under the hood for cluster. For any cluster, group replication is the main component. What it does, group replication, as I said earlier, is basically, let's go back to the diagram. So group replication happens between the multiple DB nodes. You see the GCS here. So this is saying like group replication is happening between primary to secondaries. And group replication is nothing but a data flowing between primary to secondary, but it is not using the exact port that database use. So database responds to application on 3306. Group replication uses a different port so that it will not conflict with the actual application data, and it will make sure that all the data is applicable here. Whenever there is a delay for all the sync, and what group replication does in the background, it will identify all the transactions, whatever was not done from the last sync. It will give them a group replication ID, which is called group transaction ID. And based on that group transaction ID, it will go to the secondary nodes, then it will identify whether these transaction IDs were committed or not. If they were committed, then it will not try it. If they were not, it will just load that data, those transactions to the secondary nodes. And if there is any conflict, it will resolve it back. Behind the scene, it will also modify all the group replication tables where it is holding those transaction IDs, where it has data which is secondary, which is primary, read only, and there is also a table which has all the information of members of the cluster. it will say that like how many nodes are connected to this cluster for this group replication and what they're supposed to do for each of the cluster. So that information is the metadata that is utilized by group replication. The other thing is MySQL router. Again, as I talked about it earlier, MySQL is the mediator between MySQL router is the mediator between the application and the database cluster. It could also be a load balancer. Most of the time, it has been treated as just as a shipping guy and nothing more than that. But the main functionality of it that it can segregate data between read, write, and read-only port. It is also helping operator to identify the state of the cluster because it does the health check. You see a orange arrow here, which is going down metadata heartbeat. So router, in order to get updated with the latest information of cluster, so it polls all the cluster information as a heartbeat, and it will identify like out of three nodes which one is responding and which one is not, and it will share that information with the operator so that operator can decide if there is any failure in the system or if not. So we can also customize this time delay based on the configuration, but that's how it will identify. There are also multiple ports for read only, read write. There are also different ports for secure transactions, and that's how router is very handy in order to provide an abstraction. MySQL shell, again, the API level configurations that we want to do. Technically, we are not supposed to intervene if there is any failure or any kind of disaster happening on the database. And most of the time, what people do is they try to log into the cluster or the database itself and modify a few things. But at the same time, operator is also doing the same thing or something to fix the cluster, because operator is the first guy who got to know within 500 milliseconds. It got to know that okay, something is wrong with the node. If that is wrong with the primary node, then the main task of operator is to bring up another primary and to make sure that application is not stuck, and then it can fix all the failures with the help of Kubernetes and with the help of MySQL shell, all the metrics, all the group replication data to identify the root cause and automatically fix it. If that is something which is not fixable, then it will log all the issues that this is the issue. It will try to kill the pod. It will create a new pod based on the initial configurations, and then there are like multiple parameters it will verify, and with the help of Kubernetes it can also create that new pod, and it can that new pod could be a secondary in the beginning, which is a clone of the new primary. So that's how it will make sure that all the data is latest. In the background, group replication is always working. So that's how operator with the help of shell will identify how the failures and how the transactions are happening. So this is how the group replication works. It whenever it receives any transaction, it broadcasts to all the secondary nodes on the 33061 port, which is different from the regular application port. And with the help of group transaction ID, it will identify whether the transaction was achieved, whether the transaction was committed on that particular node or not, and then accordingly it will commit or roll back. On the right side, we have the quorum rules that I talked about in the beginning. The quorum rules says like right, uh, like a cluster has to be up only with the majority of the members. If it's a 3-node cluster, then minimum 2 nodes has to be up. The principle is the same, that there has to be minimum 1 replica available on the cluster. If there is no replica available, then cluster should simply not respond. And that's why it is recommended to have 3 or 5 or 7, like odd numbers of nodes in the cluster, so that it can decide on the majority. So this is the this is the slide that I can use for the failover. And let's say, for example, something goes wrong on the router A, which is the primary router, which is responding to the server application layer. So if something goes wrong with the application layer, then application will not get to know. The first guy who will be informed is the operator, and operator will eventually modify the headless service that application layer is connected to. Of course, there could be a glitch in the application which is connected to the router, but things happen in the background, and this happens in the milliseconds, so that operator will make sure that router A is down, so router B doesn't have any backup, doesn't need to have any sort of startup or to load any data or anything. It is always ready. So within milliseconds, it will make sure that router B is responding to the headless service, which is responding back to the application layer. So that's how it will make sure if our router is down. Then the same level of failure could happen at the group cluster as well. Here we have 3 node cluster. First one is primary, second and third are the secondaries. If something is wrong with the let's say cluster node 2, then application is not stuck because primary is still responding. And behind the scene, what MySQL operator will try to do, it will try to identify the root cause for the secondary. What was the failure? If it is something on the configuration side, it will try to fix it. If it is stuck based on memory or something, it will try to fix it. If it is beyond its capability, it will try to contact to the Kubernetes and try to kill the pod and start a new pod. And that's how it will fix it. One thing to note here is that all the DB nodes are stateful set. Stateful set means they maintain a state because it's a database, so they need to save the database. Contrary to the router, where router doesn't have to save a state, so that's why the recovery is very fast. But here, whenever on the database there is a failure, because they have to save this state, they have to have the same name, they have to have the same data which is there on the other nodes. So that's why there is a recovery process which could take few seconds to minutes. It depends on the data. If we have a huge database with huge load, then it may take some minutes to clone that data to bring it up. What if there is a failure on the primary node? If the primary node goes down, then automatically router is hampered because there is a glitch here and no one is responding immediately to the router, and application is also stuck here. So in that scenario, again, within 500 milliseconds, operator will get to know with the help of health check and the router that primary is down. The first thing it will do, it will go to the secondary. It will check which secondary has the latest data. It will get that data from the group replication, that out of these two, if both are in sync, it will randomly select any of the node. If one of those secondary node is ahead of each other, then it will pick the latest one. The other one is still in sync. So that's how it will identify, and it will make a new primary out of secondary. Let's say node 3 is the secondary node which has all the latest data up to date. And MySQL operator will automatically make this node 3 as a primary node, and it will modify all the metadata in the group replication in the databases, so that router can also be informed about the new primary. So and this will happen within seconds. Then it will try to fix the primary and go to the same cycle how to fix this. That's how it happens. So why do we need to use Kubernetes and the cloud? The the first and foremost thing, like what I was talking about earlier as well, self-healing, because Kubernetes as a monitor, it will identify the root cause. It will see the pod. It will verify the failure if it is in his hands in the configuration or in the container level itself or the cluster level itself. It will try to fix it, or it will start a new pod as a clone. So that's how it self heals. And that's the biggest advantage of having a Kubernetes deployment. The second thing is declarative. Why do we need to have Kubernetes? Although we know that there are multiple components attached or there in the picture, operator, SQL, shell, router, nodes. But as a whole, for Kubernetes, this is just one image, one hand chart. Internally, there are multiple configurations. So this is just one product for Kubernetes, and internally it handles everything. So there is no complex behavior. There is no uh, uh, multiple pull requests to modify the code, or if they have to modify the database schema and all, that is eventually easier on the Kubernetes. Same goes on the rolling upgrades. If we have to upgrade a cluster, it doesn't have to be a downtime. It can be achieved via zero downtime because there are multiple nodes. We're not bringing the whole cluster down. It can be done exponentially. Like we can start with the cluster, which is a secondary node, which is standby, and that can be upgraded for the schema or for the version upgrade. Similarly, it can be done for other cluster, and then once those two secondary nodes are up, then they can then the operator can simply choose one primary for there, and it can now upgrade the primary after making it secondary. So that's how this is called as rolling upgrades, and it is achieved by zero downtime. On the right side, we have the advantages of having the cloud system. With the cloud, what we can achieve is if we have multi-cloud deployment, then the main thing that we get is the pod affinity. What that means is that the similar pod is not deployed on a single cluster, on a single site. So we're not deploying all the like application or the cluster or the database or the database volumes where we are actually saving the data on the same node, just to handle the recovery, just to handle the disaster. We should deploy it on multiple clouds if applicable, or if we have, so that if one logical site is down, if one region is down, then the other region can completely take it over, and all the replication is also happening at different geographical locations. So we are covering that aspect of failure, and that is achieved only by the cloud. Then we have the durability. Durability, how we can achieve it? Like we know that all the database have their own persistent volumes where they're actually saving the database. So instead of having that persistent volume within the same cluster, we can segregate it to the cloud so that the actual data is on a different site. So it is not attached to the cluster itself. If all the three nodes of the cluster, or all the nodes, whatever 5, 7 goes down on the cluster, we still have the data. So it's only the deployment that goes down, data is still preserved. So that's how we can achieve it via cloud. We can just spin up certain volumes or certain disks at the cloud. It could be any cloud which is applicable, and it can also respond to the live data, or it can also be applicable to the static backups. If we are taking the whole system backup, we don't have to keep it at the same site. It can be present at a different geographic location. Then the last point is the portable. If we are having the cloud, let's say for the same example, PVCs, if the persistent volumes are at a different location, then it's like very portable. We can plug and play. Today we are using Azure. Tomorrow we can use uh, Amazon services or any other cloud to save it. Underneath, if we want to change like we have the data, if we want to change the actual database to a different database, then we have the data and we can just import that data from that different site. So it's quite portable. It's like loosely coupled system. So that is also achievable when we have the cloud. The main thing is we are saving it for the recovery, a faster recovery, and to minimize the data loss. Okay, so this is the failover scenario that I have already described. When primary dies, MySQL operator will try to detect within seconds what happened, and then it will elect the new primary. It will communicate the same thing to the router, and then this is how the services are restored. All right. So throughout the session, I was talking about MySQL InnoDB cluster, but that is not the only solution. We have multiple solutions provided by multiple providers in order to achieve the database clustering aspect of any distributed database on the Kubernetes itself. So the uh, first one is Postgres SQL. It comes with its own Postgres operator, which is Galera or Percona. So this is again the same concepts are still the same, like same combination. They have an operator, they have router, they have multi-node cluster, and they have shell to work on it. But yeah, there are a few advantages and disadvantages. Then we have Kubernetes native operators, which is cloud native PG. Again, Percona operators can be used with them. Then for distributed scale out SQL, Vitess is the one, Cockroach, MongoDB is the solution that is provided by them. So I will leave it up to the audience. They can explore these options based on their requirements. And yes, that is all from my side. If you have any question, please feel free to ask.
Uh, well, I have a question. Hello?
Yeah, please go ahead.
Okay. I'd like to take you back to the slide having slide that had the application layer, router A, router B, and the clusters.
This one?
Yes, that one. I'm just confirming. I know it's very likely, but I'm just confirming that the MySQL operator should run on the controller node. Because I understand that there are the replicas would most likely be on the worker nodes. So is it the standard case that the MySQL operators to run on the controller node?
Yeah, so the MySQL operator can run on the controller node as long as it has access to the worker nodes. It is fine because all it needs to know is the metadata of the cluster with the help of routers, with the help of MySQL shell. If it has access to the cluster or to those nodes, it can just fetch all the data from the tables, and that's how it will decide like what's going on with the database.
Okay. Then one last one, just a follow-up. If I was defining all these through infrastructure as code declarative format, what will be the items that I need to specify in my, for example, Terraform? And what are the things that I won't need to touch at all?
So are you talking about the actual configurations that we need to put in the Helm chart?
Yes.
Okay. So once you download the MySQL InnoDB cluster from the MySQL website, they will give you a basic chart that will have all the components by default. It will have the MySQL operator. It will have the MySQL router. So those are the containers. Basically, those are the pods, and within those pods, they have multiple containers. So by default, you will get the router. You can specify how many replicas do you want for the router. That is configurable. Then the next part is the stateful set for the cluster, where you can mention how many clusters do you want, what kind of replication do you want. You can also configure your own port numbers. Let's say 3306 is already in use. You can modify that. You can also configure the PVC. What PVC do you want to use? PVC is like whether you want to save the data on the same pod or you want to export it outside. It could be on a different worker node, let's say, or it could be on a different cloud itself. So that is configurable. And you can also configure the backup, which is here, which is again a different pod, different service. So backup is a service that is optional, but that comes with a placeholder in that chart. That is also configurable, where you can mention where do you want to save your backups. Is it on the same system? Is it on a different cloud or somewhere else? So those things are configurable. So it's a combination of Helm charts and the configurations. That's how you can manage it.
Okay, that's clear. Understood. Thank you.
Mhm.
Hello.
Yeah, hi.
Okay, sorry. I raised my hand in the, in the call though, but I don't know. I was sorry I have to omit and talk. But since nobody called me to go ahead, so I believe I can go ahead with my question, right?
Sure. Yeah, please.
Okay. So I have like few questions. So the first one would be, I noticed the replication is MySQL database replication. So I
Mhm.
want to ask, for example, no, um, this database MySQL, right? Is it can it function? The database itself. So in this kind of setting, whereby it's been set up in a cluster, in a Kubernetes cluster with the application, feeding into the database, and the application is actually going, from the primary to the secondary databases, right? So can MySQL for a critical database, for a critical application like a core banking application, can MySQL function in this kind of setting? That's number one. So my second question is Kubernetes. Should we say, Kubernetes is actually, functioning as a load balancer in this setup here? Right. So my third question is more like, okay, I want to get more understanding of, the whole setup with Kubernetes, right? So the whole resources, that needs to be put in place. For example, if I want to set this kind of infra hub in my own organization, right? So how can I go about it, right? So those are
Mhm.
my question. Yeah.
Sure. So yeah, to answer your first question, yeah, the replication happens from primary to secondaries. If there is any transaction that was committed on the primary and the transaction completes, then automatically group replication will trigger a new thread in the background to create the transaction IDs for the group replication process, and it will take those incomplete transactions, incomplete for the secondaries. So it will take those transactions and it will replicate the same data to the secondaries, and that's how it manages. And
Okay, my first question was, can MySQL, can it function in a, for example, in a core banking application? Can MySQL function well in this case, in this kind of setting, right? Like, is MySQL reliable enough as a database?
I'm sorry, I didn't get it.
Okay, of course, there are other databases, So I'm asking to know, for a core banking application, for example, and we want to have this kind of setup, right? So I want to know if my SQL database is actually reliable, for a core banking application that receives transactions from, every day on a daily basis. Some every transaction and so on and so forth like that. So
Mhm.
my SQL, is my SQL database reliable in this kind of setting?
Yeah, you can configure your database because under the hood, it's still the SQL database. It's just that we are providing it in a cluster. So all the configurations that is applicable to a standalone MySQL instance, that is still applicable here.
Yeah. Okay. Okay. So of course, you also cited another database, I mean, in your presentation, which is Postgres, right? So you also mentioned that Postgres can be used. So I just want to know, but that is still relating to my first question. If my SQL database is actually reliable in a core banking, I mean, application environment, where Kubernetes is actually used as Kubernetes is used to set the whole infrastructure up. So is MySQL actually strong enough to undo, I mean, transactions from a core banking application in this kind of setting?
Yeah, that can be done by the shell, MySQL shell. If you want to roll back or undo any transaction, that has to be achieved manually. I mean, that is not in the uh, territory of Kubernetes because that will be a functional requirement.
Okay. So you are saying now that, the whole the whole system in terms of, okay, transactions coming into the application and eating the database, the whole functionalities is actually controlled by the Kubernetes resources, right?
Yeah, I mean, Kubernetes is just orchestrating all the transactions. It doesn't control, it doesn't control the environment. It doesn't control like what should happen with that particular transaction. Whatever the transaction comes from the application, it will just pass it on to the respective layer.
Okay. Okay. I think I get some details concerning that. So my second question is, I mean, can we say Kubernetes is acting as a load balancer in this setup?
Kubernetes itself is not a load balancer. Kubernetes
Okay.
is an orchestrator, but router, which is one component of Kubernetes, can act as a load balancer. If you want a separate load balancer, that is a different component between application and the router. So that can be achieved by the Kubernetes pod, which is Istio, Ingress, those kind of things, or any other load balancer.
Okay. So
Yeah.
router as a component of Kubernetes is actually acting as a load balancer in this setting, right?
Yeah, in this setting, it does. Because if you try to separate the traffic like read only and read write traffic, so router
Mm.
has that capability. So application can be easier on, they don't have to wait for only on the primary DB. If the read only traffic is bypassed to the secondary nodes, then the primary node has less traffic. So that's a good thing. That's how it
Okay.
achieves one layer of load balancer.
Okay. Thank you. So can you give please can you help with other load balancer that can also work? Maybe if I don't want to go with router as a component of Kubernetes, so can you help with other load balancers that can work?
I mean, you can write down your own service that can act as a load balancer, but the fact that router is talking to the operator, that makes it special here because all the routers, they are integral part of the cluster because they are providing the metadata information to the operator, which is the actual monitor, which monitors the failures and the group replication. So if you are replacing the router with your own service or any other load balancer, then just do not do the load balancer part because router does beyond the load balancer. It shares the heartbeat, it shares the metadata with the operator.
Okay.
If operator doesn't get that information, the operator will not be able to monitor the cluster. Then it's of no use. If the cluster fails, no one is there to monitor, then it's broken. It's always broken. So router is a very important component here to share the data to all the, within the application to all the components.
Okay. Okay. Thank you. So my last question is, I mean, for example, if I want to set this kind of environment up, with Kubernetes. So, I mean, I don't know if you can provide more details, maybe something that we can a go-to, maybe a go-to, documentation or something that one can actually use as a guide, right?
Yeah. I mean, this is the same example, InnoDB cluster, MySQL InnoDB cluster. You can see the documentation on the MySQL docs, MySQL website. And there they have one basic Helm chart, which you can simply deploy on any of the cloud, which has Kubernetes and capability to download the Docker images. So it's a very simple chart. You just have that chart, deploy it with the help of Kubernetes, and I think within minutes you can do it.
Okay.
If you have
Okay.
the Kubernetes, yeah.
Okay. Thank you. So, sorry, my last question. Listen, I'm just trying to get, a more, confident about the kind of database that can
Yeah.
actually
I mean,
handle.
I know. Yeah.
Yeah.
I,
That can.
I know
Yeah.
there are like
Okay.
so many things in this. I was not able to cover all those things in depth, but this is the basic fundamentals, like why we should have it, all the, initial principles, what are important things, what are the components. Once you
Okay.
deep dive or once you go to the next layer of it, then you will juggle with the actual configurations. So I would highly recommend, if you want to deploy it, go to the MySQL documentation. The good thing is you will not feel anything unrelatable. You will not see anything new. You will understand that, and it's just about deploying the chart.
Okay. All right. Thank you. Thank you for
Yeah.
the responses. I appreciate it.
No problem. And I think we are over time. So if there is no other question, uh, back to you, Samuel.
Hello, everyone. Thank you, everyone, for sticking around. Is there anything else remaining, Vanessa?
None is left. This has been a very interesting session. I loved how well detailed Mayank was. And for me, who am a beginner, it was really helpful. So thank you, Mayank, for that. And to our audience, thank you as well for making time and joining. It's been lovely and wonderful just having and meeting you guys. Thank you.
Thank you. Thank you, everyone.
Thank you so much.